Today we are going to see three-phase half-controlled converters, that is semi-converters. So it is a single quadrant converter, that is both voltage and current are positive. Previous class we have seen fully controlled converters, that will be the voltage, output voltage will be positive and negative, so that we can control the voltage from positive maximum to negative maximum. From alpha to 90 voltage will be alpha 0 to 90 voltage will be positive, 90 to 80 voltage will be negative. At alpha equal to 0 degrees, voltage output voltage will be 0 in case of fully controlled converters. Now in this half controlled converters, we can control the voltage from 0 to positive maximum alone. So it is a single quadrant converter. The output will be positive, that is the voltage will be positive and current also positive. So we can have the circuit diagram. So here we are using three SCRs T1, T3, T5 and three diodes. So here three SCRs T1, T3, T5 and three diodes D4, D6 and D2. So the numbering already I have explained in the previous case. So here T1 plus 3 D4, T3 plus 3 D6, T3 plus T5 plus 3 T8 and totally 6 devices. So 8 minus 6 it will be D2. And additionally here we are seeing the RLE load and we are having the freewheeling diode in parallel to the load. So here we are having the RLE load, that is the motor load. So in that there will be some back EMF. So instead of that we are considering this as a RLE load. So what is the difference between the fully controlled converter and the semi-converter? Means we are having three SCRs and three diodes, and also in output voltage it will be only positive, and the three diodes will be a fixed device, or it will conduct only at the fixed angles. Whenever it is forward bias, it will be conducting. We cannot vary its conduction by means of varying the firing angles as we are doing it in SCRs. So here the conduction of the three diodes will be constant for all the firing angles of alpha. So for previous case, we have seen three cases of three of our previous case. We have seen different firing angles. For each firing angles, the device conductions will be different. So here, depending upon the firing angle, the conductions of the SCR only will be differing, and the conduction of the diodes will be same for all the firing angles of SCRs. So if alpha equal to 0 degree means the same for the angle, the device diodes will be conducting. If alpha equal to 90 degree means also the device diodes will be conducting for the same conducting angle. So depending upon the firing angle, the conduction periods of the diodes will not vary. It will conduct only for a constant period. So that will be the difference. So here we can see for alpha equal to 0 degrees. So already I have told in the previous fully controlled converter. So in that, when alpha equal to 0 degree means we have to add 60 degree for the crossover point or the reference angle. So alpha is equal to 0 degree means T1 will start the conduction at 60 degrees, and the positive group of SCRs are T1, T3 and T5. So the difference, the conduction difference are the T1 will start the conduction at 60 degree, and T3 will start the conduction with a phase difference of 120 degrees. So 60 plus 120, 180 degrees, and T5 will start the conduction at after next 120 degrees, that is 180 plus 120, there will be 300 degrees. And here D2, D4 and D6. So D2 will be conducting from 120 degrees over here, and this will be the phase difference, that is 120 degrees phase difference between the each diodes. So here we can see, so T1 will start the conduction at 60 degrees, and T3 will start the conduction at 60 plus 120, 180 degrees, that is 180 plus 120, 300 degrees. The T5 will be starts the conduction for alpha equal to 0 degrees. So 60 plus 180, so that will be 60 plus 180 means that will be 240, and 180 plus 180 that will be 360, and 300 plus 180, that is 480. 480 minus 360, so that will be 480 minus 360, that will be 120 degrees. So D2 will start the conduction at 120 degree, D4 will start the conduction at 240 degrees, and D6 will start the conduction at 360 degrees. So it will be the constant one for all the triggering angles. So here we can see D2 120, D4 240, D6 360. So each will have the phase difference of 120 degrees, and on the whole we can see it will be 60-degree intervals. The device will the computation will be occurring. So this diode conduction D2, D4, D6 will be constant for all the cases. So here also 120, for alpha 90 degree it will be 120, for alpha 120 it also be, it will be 120, up to alpha 180 degree. From 0 to 180 degree the device D2 will start the conduction at 120 degrees, and it finishes its conduction at 240 degrees. Similarly, to D4 will start the conduction at 240 degrees and ends its conduction at 360 degrees. Whatever may be the firing angle, the D4 starting angle of the conduction is 240 for D4, and for D6 it will be 360 for all the cases of firing angle. But only the firing angles, depending upon the firing angles, the thyristor's conduction time or thyristor starting of point of the conduction will be differing. So in alpha is equal to 60 degree means we have to add it by 60. So totally 120 degree. So T1 will start the conduction at 120 degree. So 120 plus 120 it will be 240, and 240 plus 120 it will be 360 for alpha equal to 60 degree cases. Similarly for 90 degrees, so 90 plus 60 means it will be 150 degrees, the starting point of T1, and 150 plus 120, 270, 270 plus 120, 390, 390 minus 360, that will be 30 degrees. And for 120 degrees, if you have to add the 60 degree means 120 plus 60, 180, 180 plus 180, 120, that is 300, 300 plus 120, there will be 420, 420 minus 360 means it will be 60 degrees. It will be the starting point of T5. Similarly for 180 degrees, 180 plus 60, that will be 240, 240 plus 120, 360, 360 plus 120, that is 480, 480 minus 360, that will be 120 degrees again. So this will be the conduction tables for the different cases of firing angles. So depending upon the firing angles, the starting points of the conduction of the thyristors alone will vary, but the diode starting points and finishing points will not vary for any firing angles. So let us see how to draw these three-phase waveforms. In previous class we have not seen this. So the three-phase waveforms will be, we have to draw first one waveform, that is first phase. If it is a R phase means, so approximately I am drawing. So if it is, if you are having the graph sheets and if you are having the paper means you can neatly draw, but I am trying with the computer and the mouse. So if it is a rough sketch means, so you follow the how the way how to draw this three-phase waveform, and you can try with the graph sheets in a neat manner. So first one, we have to start the first waveform, that is starting from 0 degrees. So positive half cycle it will be up to 180 degrees, and negative half cycle it will be up to 180 to 360 degrees. It will have the peak point at 90 degrees, and it will have the peak point at 270 degrees. So the R phase waveform will be like this. So it is a rough sketch, so don't mistake me. So this will be the R phase waveforms, and for the we have to draw the inverse of this waveform also. So here we have to mark the maximum point, and this will be the inverse of the R phase waveforms, right? So this will be the R phase, and next one we have to draw the yellow phase. For that we can have the color of green, so that it is viewable. So if we take yellow means it will not be viewable, so that we are taking it as green. So it will start from 120 degrees, and it will have the maximum point over here, and this will be the this. Similarly, we have to draw the inverse. So this will be the inverse of, this will be the Y phase. And third one, it will be blue phase. So for blue, we can take the blue. It will start at 240 degrees and it will have the maximum over here, and it will have the negative maximum over here, and it will cross at 60 degrees to over this. And after this, we have to draw the inverse like this. So likewise, we will get the 6 waveforms. So first one, so it will be R phase, and second one Y phase, and third one B phase. So depending upon that, we can name it. So if it is a line voltage, means we have to name it as V. First one, it will be VAB, and the inverse of this waveform will be VBA. So the inverse waveform of this VAB is VBA, and the second waveform, we are starting it from 120 degrees, that will be VBC. So this will be VBC, and the inverse of this waveform, it will be VCB. And the third waveform, which is starting at 240 degrees, this will be VCA, and the inverse of this waveform, so this will be VAC. So this will be the 6 waveforms of the three phase, that is the line voltage we are marking. So the line voltage of the input will be like this, 6 waveforms, that is the waveforms and its inverse, 3 waveforms and its inverse. So likewise, you have to draw the 3 phase waveforms. So for alpha equal to 0 degree, we can calculate as that of the previous we have seen in the single phase fully controlled converters. For alpha equal to 0 degree, so plus 60 degree means it will start the conduction, T1 will start the conduction at 60 degree, and 60 plus 120, it will be 180, 180 plus 120, it will be 300. So the starting point of the conduction of thyristor is T1 is 60 degree, and it will conduct for 120 degrees, and the T3 will start at 180 degrees, and T5 will start at 300 degrees, and like again the cycle will repeats. Similarly, for this will be D2. So this is D2, D4, and D6. The diode D2 will start the conduction at 120, and D4 will start the conduction at 240, and D6 will start the conduction at 360 degrees. So for each 60 degree, we have to mark the conducting SCR. So first 60 degree 5,6, second 60 degree 1,6, third 60 degree 1,2, and fourth one 3, 2, 3, 4, 5, 4, 5, 6, 1, 6, 1, 2, and 3, 2. So for each 60 degree, what are the phase voltage it will follow means 5, 6 means 5 is connected to C phase, and 6 is connected to 6 is connected to B phase. So the output voltage will be VCB. And second one 1, 6, 1, 6 means 1 and 6, that is AB. That is one, next one 1 and 2 AC, that is VAC. 3, 2 means 3 and 2, that will be BNC, VBC. 3, 4 means again VBA, and 5, 4 means again VCA. 5, 4 means it will be 5, and 4 it will be VCA. Again the cycle repeats. After 360 degree, the cycle will repeat. That is VCB, VAB, VAC, VBC, and VBA. So for first 0 to 60 degree, it will follow the input voltage of VCB. So VCB means we have to mark, that is the VCB waveform. You can take the red color so that it will be visible. So VCB means for first 60 degree. So this is the 60 degree. For first 60 degree, it will follow the waveform like this. So this will be your output waveform. The outer envelope, same as that of the fully controlled converters, it will be the output voltage waveform for alpha equal to 60 degrees. So next one for 60 to 120, it will follow the VAB. So it will follow this outer envelope. So this will be your output for next 60 degree. Next one, it will follow VAC. So this will be the output waveform, and for next 60 degree it will be VBC, and it will go on like this. That is, it will follow the outer envelope of your six waveforms. That is six input voltages. The output voltage will be like this. So it will be somewhat DC with the ripples. So this will be the outer envelope will be your outer output voltage of the semiconverters for alpha equal to 60 degrees. Then next one, similarly for the alpha equal to 60 degrees. So 60 plus 60, the starting point of T1 will be 60 plus 60, 120 degree, 120 plus 120, 240, 240 plus 120, 360 degrees. But the devices conduction D2, D4, D6 will be same. That is 120, 240 and 360. So by this we are marking this positive group and negative group of tables, and we have to calculate the conducting SCRs or conducting devices for each 60 degrees. So for each 60 degrees we are marking over here. This is for 0 to 60, 56, 60 to 120, 56, and 1 to 1 2 3 4 3 4 5 6 5 6 1 2 and 1 2. So the starting point and the finishing point of the positive and negative group devices are in similar manner, so that it will have a 60 degree or a 120 degree same devices will be conducting. So for 5 6, 5 will be connected to the C phase, 6 will be connected to B phase. So VCB for first 120 degrees, and next one 1 2, 1 2 means A and C. For next 120 degree it will follow the VAC, and for next 120 degrees it will follow 3 and 4 means 3 and 4. 3 is connected to B and 4 is connected to A, that is VBA. And next one VCB, the cycle will repeat after say 360 degrees, VCB and VAC. So VCB means, so this will be your output, this is input voltage. So from 0 degrees to, and here 0 degrees to 120 degrees. So 120 degree will last up to here. So up to this, it will follow the VCB. So 0 to 120 degrees. Since it is a 5 by 2 is 90 degrees, so the next point will be your 120 degree. So up to this, it will follow the output voltage will follow the VCB. Then next 120 to 240, it will follow the VAC. So this will be your VAC. So it will increase over here, and it will follow for next 120 degrees. It will follow the VAC. So this will be the output waveform of alpha equal to 60 degrees. So next one it will follow the VBA. So VBA means it will increase over here, and it will follow the output waveform like this. So this will be the output waveform for 0 to 360 degrees. So here we have drawn for 0 to 120 it will be VCB, and another 120 that is 240 it will be VAC, and this is 120, and another 120 that will be 360 degree it will be VBA. So here we have drawn for a single cycle. Here it will extend up to second cycle. So it will have some different scale values. So we cannot confuse. So it is for a different scale. So it will follow the waveforms as per the table. Then next one alpha equal to 90 degrees. So for alpha equal to 90 degrees, so 90 plus 60 means the starting point of T1 will be 150 plus 120, 270, 270 plus 120, 390 minus 360, that will be 30 degrees. So this will be same D2, D4, D6, the starting point and the finishing point are same. So here also we'll have some multiples of 3 angles, so that we can have 30 degree conduction table. So for each 30 degree we have to draw, or we have to mark the conduction of each devices, and next we have to consolidate which devices will conduct for each 30 degrees. So first case 3 and 6, and for next 0 to 30, 60 and 90 degrees, the same devices 5 and 6 will conduct, and next for 30 degree 5 2, and for next 90 degree 1 2, and next 30 degree 1 4, and next 90 degree it will be 3 and 4. So the 3 and 6 and 5 and 2 and 1 and 4 are the same leg devices. So 1 and 4, 3 and 6, 5 and 2 are the same leg devices. If same leg devices conduction means the output will be directly short circuited. Instead of that, here the freewheeling diode will conduct to dissipate the energy stored in the inductance. So the devices, same leg devices may be conducting or if we are connecting the freewheeling diode means that device will conduct for the 0 to 30 degree period. So during this conduction of same leg devices or the freewheeling diode, the output is short circuited so that the output voltage will be 0. So for 0 to 30 degrees, the output voltage 0 since the freewheeling diode is conducting. The next one it will follow the VCB. So for 30 degrees, so here it will be 30 degrees. So after this it will follow the VCB and it will last up to 120 degrees. So that it will follow up to 120 degrees. The next 30 degrees. So next 30 degrees again the freewheeling diode is conducting. So the output voltage will be 0. Next it will follow the VAC. So it will follow the VAC up to over here. And for next 30 degree it will be 0. And next it will follow the VBA. So this will be your VBA waveform. So for every 120 degrees, 30 degree will be 0 period due to same like device conduction or the freewheeling diode conduction. So during that period, the induction stored energy will be dissipating, and the next 90 degree, the corresponding devices will be conducting. So this is for 90 degrees, where 30 degrees for 0 period, and 90 degrees it will be the voltage will be followed as per the table. The next one 120 degrees. So here also we are having some difference. So here we are having the 120 plus 60 means 180 degrees. So 180 plus 120 300, 300 plus 120 420, that is 420 minus 360, that will be 60 degrees. So for each conduction table we are finalized, that is for first 60 degrees we are having 3 6, and again another 60 we are having 5 6 5 2 1 2 1 4 3 4 3 6 5 6 5 2 and 1 2. So here we the voltage, that is back EMF will come into action. So for certain period we'll have some back EMF, and after that the voltage will be rising. So here the 0 voltage period means it will be same like devices conduction. This 3 4 3 6 5 2 1 4 3 6 and 5 2, or it will be here we can have the freewheeling diode conduction. So here freewheeling diode also it will be forward bias, so that will conduct and it will dissipates the inductance stored energy. And after that after this point, that is here, after this point VCB has to be followed, but here the output voltage will be equal to the back EMF since the VCB will be lesser than that of the magnitude of the battery voltage E. So after this point, the up to this point the E will be maximum when compared to the base voltage VCB. So it will follow up to this point the output voltage will have the battery EMF, and after this point it will be following the VCB. So after this point, so here it will follow the VCB and it will follow for up to 120 degrees, and after this 30 degree it will be 0 period, and after this it will be battery EMF, and after some time it will have the VAC, and here it will be again 0 battery EMF and again VBA as per your table. So this is for the 120 degrees with freewheeling diode and RLE load. And for the last case, the alpha is equal to 180 degrees. 180 means 180 plus 60, that will be 240 degrees. So 240 plus 120, 360, 360 plus 120 for a single phase, it will single cycle, it will be again 120 degrees. So here we can have the conduction, that is both the devices, positive of cycle, positive group of devices and negative group of devices will have the same conduction, that is T3 and T6 are from same leg, and D5 and D2 are from same leg, and D1 and D4 are from same leg. So same leg devices will be conducting for all the tables. So T3 and D6, again T5 and D2. So same leg devices will be conducting means, so there will not be any output voltage across the load. So the output voltage V0 will be equal to 0. So for alpha is equal to 180 degrees, the output voltage will be 0. So that you can vary the alpha from 0 degrees to 0 degrees, it will have the positive maximum value, and it will decrease when the alpha is increased. That is alpha equal to 60 and 90, the output voltage magnitude will be decreased. When alpha equal to 180 degrees, the output voltage will be 0. So this will be realized by means of this expression, that is V0 is equal to our average output expression for three-phase semiconverters. that is 3 pulses per cycle. For a single cycle of 1 by 2 pi, it will have 3 pulses. We can multiply it by 3, and it is VML, that is V line voltage sin omega t d omega t from alpha to pi. And we can take the VML is outside, that is a common term, and we are integrating the sin omega t. On integration of sin omega t, will get minus cos omega t. So minus cos omega t means up to the for the limit of alpha to pi. So minus cos pi plus, that is minus into minus plus cos alpha, then minus cos pi will be equal to minus 1, that will be equal to 1 plus cos alpha. So 1 plus cos alpha will be the final answer for this integration. So we 3 VML by 2 pi 1 plus cos alpha. So here when alpha is equal to 0, cos 0 is 1, and 1 plus 1 2, that is 2 will be gets cancelled. For alpha equal to 0 degrees, cos 0 1, and it will be 2 2 2 will gets cancelled. So V naught will be equal to 3 VML divided by pi. And when alpha equal to 90 degrees, V naught will be equal to, for alpha is equal to 90 degrees, cos 90 degree will be 0. So the V naught will be equal to 3 VML divided by 2 pi. So it will be somewhat reduced than the previous case. And for alpha is equal to 180 degrees, so cos pi alpha will be equal to minus 1. So minus 1 means this term will get 0. So the output voltage V naught will be equal to 0. So for alpha, varying the alpha from 0 to 180 degrees, so the output voltage will vary from 3 VML by pi of maximum to the value of 0. So we can have the control characteristics like this. So that is, this is your V naught and this is the alpha. For x-axis we are having alpha, y-axis V naught. So it will maximum to, it will reach a 0 from 3 VML divided by pi. So 3 VML divided by pi to 0 and 90 degrees. So here it will be 90 degrees. So 90 degrees will have the magnitude of 3 VML divided by 2 pi. So the controlling range will be, for alpha equal to 0 degrees, it will be 3 VML by pi, and for alpha equal to 90 degrees, it will be 3 VML by 2 pi. For alpha equal to 180 degrees, it will be 0. So the output voltage will be 0. So this will be the control characteristics of the three-phase semiconverters. Thank you.